We're making our way up and down the East Coast here, at least in part virtually. Let's head back down to Shepherdstown, West Virginia. Here we're speaking with Brian Vinci, an aquacultural engineer at the Conservation Fund Freshwater Institute. Dr. Vinci helps fish farmers design, build, and maintain indoor recirculation systems for raising salmon and trout. His research includes developing highly efficient water treatment systems, where large tanks that hold growing fish are initially filled with fresh water, and then a complex system filters and recirculates the water, which significantly reduces the need to replenish the tanks with fresh water.
With climate change, we're seeing constraints on all sorts of resources, including water. So the idea with this program is to use water carefully. Now, aquaculture in general is not a consumptive user of water. We use it, we put it out. But with recirculation aquaculture in the program here, the idea is to reduce that to the minimum possible, to be careful about it, and then capture as much waste as possible into that flow so you can treat it and remove it. And actually be able to site these fish farms close to population centers to get people fresh, high-quality seafood close to them for a lower carbon footprint.
Dr. Vinci notes that in his facility, they typically have to provide enough fresh water to replace the existing water in this large fish tank every 10 days. But with newer technologies, including membrane biological reactors, which we'll hear about later, they could stretch it to 50 or 100 days.
That's 1/100th of that water use that we are currently at. And that would be a tremendous goal or achievement for us.
Okay, let's take a tour of this indoor recirculation system. This whole building is modeled after a 1 to 10 scale fish farm. This is so the research done here can be applied directly to fish farms at scale. We start in a sort of nursery section, which looks like racks of narrow drawers. These temperature-controlled drawers are where eggs are brought in and hatched for research projects. Aquaculture farms are always asking ARS researchers to study things like fish yield, size, taste, color, and disease resistance. They start by evaluating the eggs, and once they hatch and start to grow, they're moved into these small but deep tanks where researchers study things that may affect their growth, including stressors. These tanks are constantly monitored for dissolved oxygen, carbon dioxide, and total gas pressure. Hanging over the tanks are these black plastic tarps, which allows researchers to study how different light periods can affect fish health and growth. We now move to the big tank, 40,000 gallons, where researchers can see how different conditions affect growth as fish reach harvest size. This tank is also equipped with cameras to visually inspect the health of the fish. For example, if a lesion is spotted on the head of a fish, it may alert the fish farmer of a possible disease outbreak, and they can then hopefully get ahead of the disease outbreak before it affects all the fish in the tank.
What you'll see is there's no water leaving the system today. This is essentially zero exchange system right now. To have such little water use, we have to have technologies to treat the water, to remove the waste and add back oxygen.
The tank is equipped with 2 drains, one on the bottom of the tank and the other on the side, which acts like a pool skimmer. This drain captures 95% of the flow and moves the water through a microscreen filter. This microscreen filter has a barrel with screen panels inside, and the panel openings are only about 90 microns.
All of the solids that the fish excrete or waste feed is caught on the inside of the filter, and only the water that passes through the openings, the 90 micron openings, comes out. So this controls the solids and takes them out of the system quickly. It actually creates the waste stream that a lot of our research in the next 5 years is going to look at, anaerobic digesting it or composting it.
After filtration, the water moves to a sump where the water is pumped to be treated through a biofilter and degassed. Now, these biofilters are essential to maintaining water quality for the fish. Researchers here are using a series of 6-inch wide mini biofilters to treat the water from the fish tank for an experiment with different therapeutics to test biofilter function. Now let's move on to the big boy. Here is the biofilter, a beast standing over 30 feet tall and over 9 feet in diameter. After the solids are removed and the water is pumped, the water moves to this full-size biofilter, which processes about 1,200 gallons of water a minute.
And that's the amount of flow that you have to remove the ammonia to keep it low enough for the fish. The biofilter itself has sand inside, and the bacteria that convert ammonia to non-toxic nitrogen live on the sand or attached to it.
Once the water flows out of the top, it's aerated to remove carbon dioxide. Oxygen is then added, and it flows back into the fish tank. Dr. Vinci likens the recirculation system to a greenhouse for fish.
We're using the ability to treat the water inside a structure to create the controlled environment. We can keep the conditions for the fish, optimal oxygen, optimal ammonia, optimal carbon dioxide, hopefully optimal everything to allow the fish to have good health and welfare, because that's a primary thing for us. But then to do it in an efficient way, really anywhere. Similar to a greenhouse where you control the environment and can grow tomatoes in Maine or Canada, you can grow Atlantic salmon, a cold water fish, in Florida. Now they have to chill their water because they're in Florida, but they're able to do that because of the technologies that have been developed with ARS support here.
In addition to developing recirculating systems, researchers here are testing different strains of fish that could be optimal to grow in these indoor systems.
And that's important because we're seeing a boom in construction of these facilities, and the genetic strains that those farms are using are really strains from other types of aquaculture, flow-through or net pen salmon culture. We're working with ARS scientists both in Maine and here in West Virginia to improve strains for performance in the recirculation systems.
We've been talking a lot about growing fish with bigger yields and consistent size and flavor, but what about their waste? Now, you may think waste from a single fish isn't a big deal, but when you're raising tens of thousands of fish that weigh 4 to 5 pounds or more, well, that's a ton of waste, maybe several tons. A byproduct, so to speak, of Dr. Vinci's work is turning that waste into a valuable product for fish farmers, such as biogas.
So in other terrestrial agriculture like dairy, they will collect all of the manure, they will digest that manure to create methane, and then use that methane to power the electricity used on the farm. And so we're looking to use that kind of technology here for contained fish farms because we capture all the waste. It's easy for us to do that, and the idea is to do something with it.
This secondary revenue stream only adds to the benefit of building a recirculating fish farm. However, Dr. Vinci sees the primary benefit being able to provide consumers with a variety of local, fresh fish. We're talking fresh salmon in Florida, fresh sea bass in Connecticut, and how about fresh steelhead in New York City?
I think making fish more common, increasing production overall for the consumer will help Americans get to that 1 to 2 seafood meals a week for the public health benefits. Because right now, Americans lag globally in seafood consumption. But if we can bring it more to the U.S. and it's American grown, I think we'll actually lift the boat for all of us.